This is a continuation of the challenges of interstellar travel. The vacuum of space. The Earth's atmosphere exerts pressure on the human body, about 1,013 millibars, 15 pounds per square inch. In the vast space between celestial bodies, there is no atmosphere, thus no air pressure. We have evolved to live and be healthy at precisely the pressure that surrounds us on Earth. Anything outside of this pressure has a negative effect on our body. A significant drop in the atmospheric pressure in direct contact with our bodies would cause gases to expand, leading to ruptured lungs and other tissue damage. Body fluids such as blood and saliva would begin to vaporize, causing swelling and severe tissue damage. And without a suitable atmosphere to mediate temperatures, the body would face extreme cold on the shaded side of solar planets and intense heat on the sun-exposed side. And without the Earth's protective atmosphere and magnetic field, one would be exposed to harmful solar and cosmic radiation. Any unprotected space dweller would experience this lack of pressure, where body fluids start boiling at normal body temperature, followed by swelling and impaired vision due to the effects on the eyes. Decompression follows, a sickness similar to the bends experienced by some divers when nitrogen bubbles form in the blood and tissues. Rapid decompression could cause significant cellular damage and rupturing of cell membranes. Due to hypoxia and other effects, a person would lose consciousness within about 15 seconds. Due to these, the mission and spacecraft would have to be designed to get around the problem of no atmosphere and no pressure in space. This can simplify some mission aspects while complicating others. No air pressure may facilitate movement of the craft and people, but would complicate having to provide a constant atmosphere and air pressure within the habitable areas of the spacecraft and spacesuits. We currently do have systems that reliably provide suitable air and pressure for habitation. On Earth, large structures like the
Biosphere 2
complex from the University of Arizona somewhat achieve this. But most Earth structures merely transfer air and pressures from the natural environment to the interior of the structure. In space, the atmosphere needs to be manufactured and maintained, and these would have to be much more reliable and robust than Earth's for a long-duration interstellar mission. Additionally, to provide pressure and a livable atmosphere in a kilometer-scale structure in space is no easy task.
Massive amounts of complex atmosphere and pressure equipment will be required, adding to the weight-to-orbit needs of the mission. Additionally, we have little experience with these large-scale systems in space.
Space collisions. Interstellar travel requires high speed, relativistic or not, to make any reasonable progress and have a better chance of reaching another star system. Much higher speeds than currently achieved by our fastest spacecraft will be needed. However, these higher speeds also increase the chances of collisions with space particles. Although few and far apart, micrometeoroids are present in space, along with other even larger bodies. These can cause serious spacecraft damage even at relatively low speeds. If relativistic speeds are reached, then collisions become more damaging, and particle sizes that can cause damage also decrease. This means that even dust particles can cause damage at very high spacecraft speeds. So, for these, shielding must be part of any interstellar mission design. Physical shields or active force fields that protect the spacecraft while in high-speed travel will be an absolute requirement on interstellar voyages. As for physical shields as an added advantage, these may double as radiation shields for the ship and its crew. But the sizes and materials to be used are just outside of our current space manufacturing capacity.
Lastly, there are many unknown challenges that will be encountered in an interstellar mission, some that deal with the nature of space and time and all of the phenomena within. With much luck, space phenomena may be discovered or understood during our research efforts en route, such as radiation sources, dark matter, dark energy, etc. With less luck, these and others may remain mysteries for ages or may never be understood. And without understanding them, or even effectively detecting them, many harmful space phenomena may harm us. The unknown's ill effects may cause much harm to unsuspecting and unprotected interstellar crews. For example, we may unsuspectingly fly right into harmful areas of space yet to be discovered. Or we may veer off course due to our ill understanding of interstellar trajectories. Long-held ideas and theories may be erroneous or faulty, and current laws of physics may need to be revised. With luck, these adjustments and learning will happen without compromising the overall mission.
Thank you very much. Please look for the next episode on this series very soon.